Hello, this is Mike at Gamefromscratch, and today we're going to be looking at using cameras and viewports in LibGDX. If you've been following the series up till now, we've just been using whatever the device's native resolution is. So we're working in raw pixel values, the width and height of the viewport or the device that you're running on, and for several projects this works perfectly well. However, once you start talking a game that's going to run on multiple devices or potentially multiple resolutions on the desktop, working in pixel coordinates has suddenly becomes a much worse idea because the coordinates only work on that one initial device or resolution and don't work well at all on other devices. Fortunately, LibGDX has a pair of solutions out there that make this quite a bit simpler. One is the camera, and the second is the viewport. There's another option as well where you can deal with multiple resources of different file sizes for multiple resolutions. It's something we'll cover at a later date. But today we're going to be looking at the camera and the viewport. The camera can be thought of as the viewer's eye in the world. Even though you yourself might be working on a 2D game, behind the scenes, LibGDX is actually working fully in 3D. And the camera is what tells LibGDX what part of your world or your scene to render and where. A viewport, on the other hand, is like the aspect button on your HD TV, assuming you have an HD TV, and I think everybody does at this point. But you know, when you have, say, a single definition signal coming into your TV, the aspect button helps determine how it'll be displayed. You can either watch it as like its original size as a little stamp in the middle of your screen, you can stretch it out, you can try to scale it or zoom it. That's basically what a viewport does. So you got the camera, which determines what's seen, and then you've got the viewport, which determines how it's seen. First, let's deal with the camera. In LibGDX, there's actually two kinds of cameras. There's the orthogonal camera, and then there's the perspective camera. They both kind of come back to the concept that the human eye, as things go farther away, sees things as getting smaller. And in that case, this is mimicked on a 2D screen, on a flat screen, using a perspective camera. So pretty much as something is drawn further away, the perspective camera makes it smaller and smaller. Whereas an orthogonal camera is the same size regardless. An easy way to actually illustrate this is to see it in 3D. Here is Blender running, and here is the default cube in a perspective view. And as you can see, it's not immediately obvious to you because the trick is doing its magic on your eye. But this edge and this edge aren't the same size. As you get further back, this gets smaller. And it's even easier to illustrate if I go in here, oops, I grab that face, this, and I bring it towards the vanishing point. So as you can see, this is getting smaller and smaller as it gets away from the eye, and that's what a perspective camera does. On the other hand, an orthogonal camera, same size. I made that too big, so it's off the screen, but as something goes further back into the scene, it's drawn exactly the same. Now, when you're working on a 2D game, what you're really doing, here, let me shift to a side view, is you're just making image after image after image, and you're pasturing them on to basically a grid. So this is a textured square, and that would be your sprite. And then if you have multiples, so let's just go ahead and create a copy of this guy. Each one of these would be like a textured, they overlap like this. This is the only thing your z-coordinate is used for, determining what's in front of something else. So when you're trying to decide between the camera to use when working with LibGDX, if you're working on a 2D game, you want an orthogonal camera because as it gets farther back in the scene, you actually want it to always be exactly the same size. However, if you're working on a 3D game, you're going to want to use a perspective camera because orthogonal just looks weird. If you're using a perspective camera, there's actually a few more options available, such as you can set the field of view, the far off, the near and far lens, and those kind of things. They're unimportant to us in this. We're going to deal mostly with 2D right now. If I do a series down the road or a couple parts down the road on 3D, I will cover perspective camera in more detail then. So let's go ahead and actually look at an example. What we're going to do is we're going to create a world. There's one big image in the background that's going to compose the entirety of our world. And then we're going to create a camera that works over top of it and pans around. Here's the graphic I'm using. This is quickly drawn in Paint. Here is our game's world. And now I'm going to go ahead and I'm going to load it into the load it on the screen and then create a camera that looks at it. So let's go into our code. So we're going to want to do some positioning and sizing because we're going to start using arbitrary dimensions instead of pixels dimensions. So instead of using a texture, I'm going to go ahead and use a sprite. Like so. Get rid of this texture call. So instead what we want to do is make our new sprite equals new sprite, which is going to need a texture, which is internal, and I believe I called it the world.ping. Okay, so we're loading our sprite into the world. One thing I should notice here, and I won't do this in the future, I will leak memory like mad while I'm working on this stuff, but you'll notice I set the texture of this sprite in its constructor. Well, one thing to be aware of, texture is disposable, but sprite is not. So when the sprite goes out of scope here, you will lose your texture. The memory you used in texture will now be gone. The obvious answer to this is you have to dispose it, and you can do so implementing expose, and then for your sprite, call get texture and dispose it that way. So even if you don't keep a reference to your texture variable, you can dispose of it this way when you're done. So now the final thing we've got to do here is just go ahead and draw our sprite to the badge. Like so. Now I got to create a run configuration. Yeah, this is a desktop project. The assets are in the Android's asset folder. And our main class is desktop launcher. All right. So this is all predictable. We've done this many times. There is your scene, your sprite just drawn on screen. Apparently run twice for some reason. All right, let's close down the second one. So now let's add a camera to the mix. Now that we've got the assets handled, I'll just kick into presentation mode so it'll be a little easier to follow along. So the next thing we need to do is go ahead and create our camera. Let's graph camera, like so. And now we go ahead and create it. For now, we are going to use the screen's dimensions for our camera. Equals new ortho camera. So GDX graphics get width. And GDX.graphics.get height. Now, if you're thinking to yourself, well, isn't that the exact same as using pixel coordinates? Yes, it is. Don't worry, down the road we're going to go ahead and change that. But for now, we're going to make the width of our camera the same as the width of our resolution. So that's set. So the final thing you need to do now is tell the batch which camera to use. And that's done by using set projection matrix. Now, a little bit of explanation of what's going on here is behind the scenes, once again, as I said earlier, LibGDX is actually a 3D engine doing 2D work for you. And as part of the transform pipeline that goes on with OpenGL behind the scenes, there's two major matrix multiplications that happen. One is the world projection, which is what translates or all of your 3D objects in space to where they should be. The second one is the view projection, which then takes the results from that and translates those to be on your screen. So the camera actually creates those. And if we look at this, we've got the projection, matrix 4, and the view, matrix 4. Now the neat thing about matrix math is when you multiply them together, you get the results of doing both. And that's exactly what we're going to go ahead and do by using combined, which is projection times view. And that formula itself will be applied against all the sprites in your scene to first translate them in 3D and then to screen. So that is what calling camera.combine does. So now we're going to go ahead and run this. And you're probably not going to get the results you thought you would get, but you will get results. Here we go. Okay, so what's happening here? Key concept to understand here is the camera itself has a position, and it by default looks at its center. And what this is doing is looking at coordinate 0, 0. So what you need to do to offset your camera, so our world is actually here. And all we need to do is translate our camera so its center point is actually looking at the center of the world instead of at the bottom of the world. And that's just a matter of taking half the viewport width and half the viewport height and adding them to our camera's location. We can do that with camera, translate, and then we just do camera viewport width halved and camera viewport height halved, like so. And now we go ahead and run this. And it does not work. 1 second. Oops. All right, so now that our camera's translated, and this is very key, and this is why it did not work, whenever you move your camera, you need to update your camera. So in your render loop, add the line camera update, like so, and now your camera will move and update and be rendered accordingly, like so. So now we have the bottom left of our world being shown in the camera. Now what we want to do is get away from using device coordinates. Instead use coordinates that will be the same across all platforms, environments, and such. And those can be completely arbitrary. So let's go with, what do I want? Interfloat. I'll go with float for now. I'm going to probably want with int later, but a game world is 2048. Oh, wait, no, I don't want to use pixel coordinates. And I should probably actually give this a name that makes sense. So, what we're instead are going to do is say our game world is 100 units wide. And 50 units tall. What are those units? Absolutely nothing. Completely made them up. I went with the ratio I did because our original source image is 2048 by 1024, so it's twice as wide as twice as high. So we're staying with the basic world amount, but those actual numbers mean nothing. Only important part is that you stay consistent in how you use them. So now what we want to do is we want to create our camera to be a portion of the actual screen. And what I actually want to do is make it so that our viewport is 1024 high, so we can see all of it vertically. But when we pan left and right, we're going to see portions as it comes. So now that we have our world coordinates here, our world dimensions, we have to set that for our sprite. We want our sprite to be the same dimensions as the entire world itself. We just go in here and go set size, not scale, size. Big difference there. But we're going to set the size, and we're going to make it game world width, and then game world height, like so. So now our world is as big as the world can be, and now we want to go ahead and create our camera's dimensions so that they're not using pixel resolutions, but they're using portions of our, they're speaking in proportion to what our game units are going to be. And the first thing we're going to need to, in order to solve that, is the aspect ratio. Aspect ratio is a very critical thing that we're going to be discussing here, and it's going to be more and more important. It's actually more important, the aspect ratio is more important for a cross-platform game than the actual width or height in pixels. Aspect ratio is the ratio of the height of the screen to the width of the screen. It's very common in like high definition screens. You'll hear them called 16 to 10 or 16 to 9, which means there's 16 dots one way to 9 pixels the other way, or dots the other way. 16 to 10, and then you get really high, stupid resolution stuff like 21 to 9. Or you've got kind of the old school resolutions from the way monitors used to be, and coincidentally the way iPads are now, which is a 4 to 3 resolution, which is much squarer than you've got. And then you've got the new BlackBerry Playbook, which is actually a 1-to-1 resolution. So for every pixel one way, it's a perfect square. So it's a one pixel to the right, 1 pixel down, and so on and so forth. So what we need to do is calculate that aspect ratio. The aspect ratio itself can be calculated via, let's go, aspect ratio. We're going to need to cast this. And that is simply get the width of the graphics. Oh, sorry, we want to do the height of the graphics divided by graphics. Get the width, like so. So now we have the aspect ratio, which is the number of pixels in one way, height pixels to width pixels. And now we're going to use that value. All right, I did something wrong there. Why are you mad at me? Suppose an equal sign is useful. There we go. So that calculates our aspect ratio. Now we actually want to use the aspect ratio as part of our world. Like I said, we want the height to be the height of our world. So that would be this guy here. So in declaring our camera for the height value, go ahead and say you're 50 units high. So we'll get the entire height. Now we want to get the width to be relative to that. That's a matter of, we'll use the same amount times the aspect ratio, like so. So now we'll have a 50 by 50 viewport at the center of the screen. All right, so that should do it. Let's go ahead and run that. All right, so we get a camera relative to the center. Now let's move to the center of the world. Instead of doing this, we will now go camera.position.set, and we will make that in world units. Game world width halved. Game world height halved, and no Z coordinate. Like so. Alright, I'm doing something wrong. Oops. Alright, I pulled another stupid autocomplete error here. I obviously wanted to center the camera, both width and height, not height twice. Sorry about that. So we've set position our camera to the center of the game world, and then go ahead and run that. And we shall now see our camera, full height of the image, center to the world. Now let's go ahead and add an input processor so we can use the arrow keys to move our camera around. And that's a matter of implements input processor, wait for a little light bulb. Put all the methods in, and we want on key down. If key code is camera.translate. So we'll move one to the left, on the left. Oops. Now I've learned nothing about cut and paste errors, so I'm going to go ahead and create another one. And this time we want right. All right, why are you not auto-resolving? Obviously this setting is now disabled. Press Alt-Enter to pick it. Enter to pick it. All right. So now, again, we had an ambiguity for imports. So I don't have auto import set on it since the last update. It seems it blew it away, which is irritating. But anyways, so we check that the key is the left key. If so, we translate the camera one to the left, 1 unit. So there are a total of 50 units from the far left to the far right. We're going to be moving the camera in one of our arbitrary units each direction. Let's go ahead and run that. Now if I hit, Alright, lots of mistakes today. I'll go back to my crate, and we actually have to register our input processor. So, alright, now when I run it, left arrow, we can see the world pans to the left until we have nothing left to draw, which is where you're seeing the GL clear screen color being drawn where there's nothing there. And then if we pan our camera to the right, we shall eventually see the other side of the image. Yeah, any day now. There. So there's how you see controlling a camera, adding it to the world, proportioning it relative to the aspect ratio. And you may notice it looks all nice and good, exactly as we want it to, but we right now have actual control over the resolution, everything that came in. So now let's say, what happens if we were dealing with a different resolution here? And that gets trickier. So let's go ahead and change the resolution. If you didn't know about this already, you can actually, out of presentation mode for a second, in your the native implementation of each application for both HTML and desktop, you can set it there. So let's go into the, it won't be running on Android. It's too hard to show you on this way. So let's go ahead with the desktop. Go into the desktop launcher. You can set the resolution via using config. Now let's see what happens if we have a slightly different looking resolution. So we're going to go twice as wide as high. There's not too many devices out here with these kinds of resolutions. Sony made a double screen phone that had it. There was a couple earlier phones that did, but this is a pretty extreme example, but it does show the effect that the different aspect ratio is going to have on our scene pretty immediately. Let's go ahead and run that. And as you see now, we are incredibly stretched. That's the default behavior of the camera implementation in LibGDX. This is where viewports now come in. And as I said earlier, a viewport is pretty much the analog to the aspect ratio button that you would have on an HD TV remote. And we determined, so on the 800 by 400 device that we're seeing here, what we probably would rather have is black bars on each side. So let's go ahead and create a black bar viewport that implements on this one. So we go back to our camera demo. And first things first, we go ahead and we add a viewport. So. And then after we've gone ahead and created our camera, so one key difference that we're going to do here is we no longer set the resolution of the camera like we did here. Instead, we do this with the viewport. Now, our viewport is going to be let's move that down a little bit. Viewport equals new. And what we want to start with is something called a fit viewport. Like so. And then we want to make it, what did I use before? All right, I should not have deleted everything already. Let's go with the same resolutions we were using before. Here's what I'll do. Viewport equals new fit viewport. And that's the resolutions we want. So we're going to use the same resolutions we did before. Now, there's one other parameter here that you pass in the viewport, and that is the camera to apply against. And next, somewhat critically, like calling update, you have to apply the viewport. I suppose I should also name the viewport correctly using apply. Now, most importantly, though, when there's a resolution change on in LibGDX, there's actually a method called, and we need to deal with it, and that is the resize. So public void resize width. Oops. Float width. Float height. That, and that will be called when the resolution changes. And what we need to do there is update our viewport, which is update, and we set it to the new width, new height of our screen. Why are you complaining? You must not be ints. Which they kind of made everything floats, to be honest, because it gets confusing at times. And what we probably also want to do is reposition our camera. Like so. Right, so viewport's created, it's a fit, it's applied, set to our camera, and then on the resize we handle the update and we position our camera again. Now let's go ahead and run that. And there you see, it did its best attempt to fit the best to the device as it could. Now we've got an extreme mismatch in aspect ratios going on here because of how things are set up. Plus I think I may have just made a mistake. Just a second. Yes, I did. And you know what? It has to be something new in IntelliJ that's causing this to happen. Because the exact same error as before, the width and height were identical. So that was a little bit more extreme than I intended. There you go. So now what it's done is instead of trying to warp it to fit the aspect ratio, a very 800 by 400 screwy aspect ratio, it just letterboxed it. You're probably familiar with this, again, from HDTV. It's the same concept. So that's what a fit viewport does. There's actually a number of other viewport options available. Another one is called fill. Let's go ahead and show it in action. All right, let's run that. You see fills in as best as it can. You're going to have some cropping here, however. The next one you've got is stretch, which will, to the left and right, expand out the image to... you're doing this. Why do you keep doing this to me? There's something really screwed up with my import settings. That's why it keeps doing this to me. I'm going to have to look into that. But go ahead and here's stretch. This is pretty much back what we had when we started before, but it will stretch the image to make it match the dimensions as best as possible. Next up you have extend. So, which will, let's see it. Oh, in this particular case, it's not going to make a whole lot of sense because the aspect ratios go. But what extend will actually do is stretch out the viewport, or let me see. Yes, it'll stretch out the camera to fit everything in it. In this case, you're seeing the entirety of the screen. Finally, we have one last one, and this is the screen viewport. And yeah, screen viewport takes one parameter, I think. It takes the camera only. And this one's going to give you somewhat screwy results. There. And you might be curious, like, what exactly is happening here? Well, when you pick the screen viewport, it's just like you're working in pixel resolutions again. When you set a viewport to be a screen viewport, it just takes the width and height of the existing device and uses that. So earlier on, when we actually set our screen up to be our arbitrary units, which is like 100 by 50. Now what's happened is those units just became pixels again. So when you set a viewport to be a screen viewport, it uses whatever the native device resolution is, sort of the equivalent of having done nothing at all and just going back to using pixels again. So that's what a screen viewport is. Now let's switch our resolution for a second to be less extreme, but a more common resolution, which is, this is the 4:3 resolution of the first generation iPad. It's 1024 by 768. Now, let's go ahead and run it. Well, screen's going to come up almost exactly the same. Your dimensions are going to be off a little bit, but it's still going to be 100 by 50 pixel image in the middle, because again, it just took the resolution of the device and used it for the coordinates. The fit viewport, and now we need our coordinates again. Because keep in mind, earlier we were passing in a wider image than we had before. So what it did is it put the letter bars on each side. Now when our resolution is more vertically challenged, what it's done, or it's got more vertical space, fit in turn then does the letter bars at the top instead of each side. And then we'll do stretch. Like so. Stupid thing. Yeah, I really do not like the changes that the most recent IntelliJ update has done to my settings. So go ahead with stretch, and you see it stretched it to match the dimensions as best as possible. But you can see over here, the bits of the sun have been cropped off. And finally, we've got fill. And it fills the screen as best as possible from the source. The difference is obviously you'll play around with which one you like the best, or somewhere down the road we can actually look at loading different assets based off of different resolution. Because what you're going to run into is if things are like on a 4:3 screen and created for 16:9 aspect ratio, your results can look a little stretched, which pun not intended. These different aspect ratios could definitely have their upsides and their downsides. Which one you actually want to use, completely up to you, or you can use none at all. In that case, what you end up doing is you create a version of your game for each aspect ratio you're going to support. And then you create basically a binary. So you make a 4.3 version and a 16:9 version or 16:10 version. Now between 16:9 and 16:10, which is pretty much most of your Android devices, you can get away with just doing a stretch there. Like the difference between 16:9 and 16:10 stretch is really minimal. So in that case, what you probably want to do is a stretch viewport to stretch out the remains, because I personally hate letterboxing. I do not put bars down the side of the screen. The only time I ever want to see that is if I'm like watching a film where it's a very wide shot. And personally, I wish they would stop shooting things that way and actually shoot towards the devices people own as opposed to some arty concept that they've got in their head. But that's me ranting. So I don't like the letterbox approach, especially when you're dealing with a computer that can generate these things on the fly for you with a pretty good results. So between a 16:9 and 16:10, just do a stretch, in my opinion. And then the 4.3 versus the widescreen, I think it's actually better off for you to create a binary for each one. So that is, you actually create an iPad version specifically for those resolutions. Your code's going to be exactly the same, but your assets are going to be a bit different. And as I'll show later on down the road, there are ways to handle file loading so that your same code deals with your same code works exactly the same, and your camera coordinates will take care of everything for you. It's just the assets that are chosen will be chosen relative to the device that are run on. So there is stuff built into LibGDX that makes that easy to work with, and I'll cover that somewhere down the road. That's your various different options. So basically, to summarize, once again, your camera is your viewport into the world. It's what's going to get rendered. It's passed into the sprite batch by using the set projection and sending in the combined value, which gives you your projection translation view and your your translation and your view translations combined together, which then translates things into 3D and 2D onto your screen to be displayed to you. There are two types of cameras, the perspective and orthogonal. Chances are, if you're working in a 2D game, you want to use an orthogonal camera. So then what you run into is different aspect ratios, and they can be dealt with by using a viewport. We've shown you how you create a viewport. A viewport is simply created. Behind the scenes, if you're an OpenGL guy at all, you're really just setting the GL viewport and applying it to the transform matrix that your camera is providing. So GL viewport is something it's built into OpenGL, and it's what you're making use of here. There's various different kinds of the viewport translations you can fit to bring your letterbox style, your letterboxing of it. So you've got the bars down each side so that your aspect ratio matches your original content aspect ratio, although obviously your full screen isn't used. You can stretch, which will take your source content and warp it so that it fits the screen the best, or you can fit, which will try and put as much content on the screen, but you will get clipping off. Or of course you could create your own translation if you really want, just inherit from viewport and implement it as you wish. Once again, probably your best bet is to take widescreen ones and do a stretch. So make your assets for 16 to 10 and then stretch to match 16 to 9. The logic on that one might be reverse. But anyways, for those two resolutions, the stretching won't really make any result on how things look. However, for the difference between 4.3 and 16 to 10 / 16 to 9 is pretty perverse, and we'll probably look at how to deal with that a little bit down the road. So that's how you deal with a camera in LibGDX, or viewports in LibGDX. As you can see, once you move to an abstract coordinate system, moving between and across devices, across resolutions, is quite simple, but the strategy you actually want to take is a little bit more tricky to figure out. The easiest thing would probably be to do is to load up your art, take a look at how it goes, and try the different viewports. As you saw, switching between them was literally one line of code. So try the one viewport, see what works, find one that you like. If you don't like any of them, stick with the original. Or again, you can, if you want to work in screen level coordinates but still use a viewport, there is the screen viewport, which basically overrides all of it and just uses the screen's native resolution as the parameters to the viewport. So that's the basics of working in cameras and viewports in LibGDX. Supporting multiple devices isn't really that awful. It's just when you start looking at some pretty extreme differences like the 4.3, that's when it starts getting a bit tricky. But supporting all the other devices should actually be fairly simple using this relatively easy technique. Hope you enjoyed that. Thank you. Bye.